Now let's talk about stringed instruments. In an orchestra, basically it's divided into these four main kinds of instruments: strings, brass, woodwind, and percussions. And so in the next couple of days, we will talk about each of these individually. So let's talking about strings first. Stringed instruments. String instrument is a musical instrument that produces sound by means of vibrating strings. The most common string instruments are guitar, both acoustical and electrical, violin, viola, cello, bubble bass, banjo, mandolin, ukulele, and harp. The history of the stringed instrument dates back to about 3000 BC, and a great deal of work formalizing and developing mathematical analysis of music was done in medieval times and perhaps even earlier. The earliest known form of string instrument is the harp, and its existence can be traced back to 3000 BC because of the funeral practices of the ancient Egyptians found on tomb paintings and grave relics. Types of strings. There are two main types of strings, ideal and real. Ideal strings are perfectly uniform strings with uniform density and are composed of a uniform material that has no imperfections of any kind. This string, which is also the ideal string, is perfectly flexible. These offer no resistance to bending and have zero stiffness. So with zero stiffness, the restoring forces come entirely from externally applied tension and air resistance. Real strings, on the other hand, deviate from this ideal behavior due to damping forces. These damping forces introduced some level of inharmonicity to the system of vibration. Inharmonicity is the degree to which an overtone departs from its parent tone. The inharmonicity of the tone may be small or large, and it depends on the string itself. A thin string has an almost ideal behavior. However, as you make the strings thicker and thicker, they behave more like cylinders that have natural resonances that are not whole number multiples of the fundamental frequency. Types of playing techniques in a string instrument. So there are different types of playing techniques for string instruments that include bowed string, plucked string, or struck string. So for example, for a bowed string, we would use an example of a violin. A plucked string would be like a harp, or a struck string would be like a Hamel dulcimer. How do you change the pitch in a stringed instrument? There are multiple ways by which we can change the pitch in a string instrument. We can change the material of the string that it's made out of. Like for example, the commonly used example is in a violin or in a guitar. Tension by the means of tightening it up or loosening it down. Or we can also change the effective length of the string, right, in order for the player to play the notes. So what is a bow? A bow consists of a specifically shaped stick with other material forming a ribbon stretched between its end, which is used to strike the string and create sound. In Western tradition of bow making, bows for instruments of the violin and viola family, a hank of horsehair is normally implied. These days, usually it is plastic. The slip and stick of a string against a moving bow are determined mostly by friction between the horsehair of the bow and the string. The force of friction between two objects is less when they are sliding past each other than when they move together without slippage. Once the string begins to slip, it moves rather freely until it is once again captured by the string. So for example, this is a very good example of a slip stick action. So you can see the spots where it sticks, and then you can also see the spots where it bends. So here's where this sticking happens. The wave moves forward, comes back, and this is where the slip happens. You can also see the forces as determined by this graph over here. Large force, small force, as well as the speed. Bowed string instruments. The modern violin consists of about 70 parts. These parts include the belly, the back, the ribs, the inside blocks, inside lining, bass par, parfing, fingerboard, neck, scroll, nut, tailpiece, loop, buttons, pegs, strings, bridge, and the sound post. The violin body is a hollow box which measures about 35.5 centimeters in length. The back and the neck and the ribs and the bridge are usually made out of maple. The belly lining and the sound post are usually made out of spruce. If you wanted to look at a violin decomposed, this is pretty much what it would look like. The top half, the bottom half, the bow, and the fingerboard. The primary role of the bridge is to transform the motion of a vibrating string into periodic driving forces applied by its 2 feet to the top plate of the instrument. However, generations of violin makers have discovered that shaping the bridge is an easy way to alter the frequency of a violin. Violin bridges typically have strong resonances around 3,000 and 6,000 hertz. These resonances can easily be changed by cutting the wood at an appropriate place. Modes of vibration of a violin top and the black plate visualized by a hologram. So these are all, the top plate and the bottom plate resonances. One of the other things that we could be doing is using the Claudini plates, as we talked about before. 6 low-frequency modes of a vibration of a violin are given here. We are not going to go into too much detail, but I just wanted to show these to you. Again, C1 and C2 radiate little sound, although they contribute to the feel of the violin. More resonances. So the F-holes of a violin form the opening of the cavity resonator, also called the Helmholtz resonator, which resonance curves shows below enhances the frequency close to the open string. Now, if we're mathematicians and we're taking a physics class, what we need to do is, can we find the resonance at which it will resonate? And the answer is absolutely. An air cavity will exhibit a single resonant frequency. If the air is pushed into the volume and released, then the pressure will drive it out. But acting somewhat like a mass on a spring, which is pulled down and then released, it will overshoot and produce a slight vacuum in the cavity. The air will oscillate in and out of the container for a few cycles at natural frequency. So frequency is equals to the area of the opening, the volume of the cavity, and the length of the opening port. So the frequency actually depends on the square root of these factors and the speed of sound.